good.
So, how's your evening going on?
Yeah, everything is good.
Okay. So, please tell me something about yourself, the kind of projects you have done.
Actually, I started my VLSI career in 2020 from RV Skills. There I did some internship. It was a paid internship.
Mm-hmm.
There I did some standard cells in a 90 nanometer, SRAM in 20 nanometer, and two-stage amplifier in 180 nanometer. After
Okay.
that, I joined Mirafra Technology. There I was
Mm-hmm.
working as a buffer for a Max Linear. I was not properly on the client.
Okay.
So I got some projects in a 40 nanometer, like I did their flash ADC, LDO, and mirror
Mm-hmm.
full adder and some standard cells as well. After that, I
Okay.
joined Sign of Semiconductor.
Mm-hmm.
There I worked on 16 nanometer, 28 nanometer, and 7 nanometer. There I
Okay.
completed few models of PLL and ESD. In ESD, I just completed the diode parts like HIA diode, drain baluster diode, gated diode, and back-to-back diodes.
Okay.
Apart from this, I worked on a level
Mm-hmm.
shifter, and BGR I completed two regulators like AV Reg and HB Reg, and one amplifier I completed there. And I
Okay.
also worked on a high density standard cell and high performance standard cells in 28 nanometer, 16, and in 7 I worked only on high performance. And in 16 and 28 I completed a high density and high performance both, and completed a few digital blocks as well.
Like,
I also worked on physical verification on ICC2 shell.
what
It's
kind
a
of
synopsis.
digital blocks you have worked on?
Digital blocks, actually, I don't remember exactly.
Mm-hmm.
Their names are different. So,
Okay.
I worked on different types of D flip flops, like 7, 8 types of D flip flops, 4 types of different muxes also.
Mm-hmm.
And in a digital blocks like clock gen is there, counter logic is there.
Mm-hmm.
I also completed like only the base DRC I completed for the oscillator and HB range also in 7 nanometer.
Okay. So, what's the actually, what does clock generator do? What's its purpose?
Uh, it generates the clock actually.
Okay. Anything, do you want to explain it in a bit more?
Theory concepts I don't know about that clock generator.
Okay.
That's only like to generate the clock pulse. So that clock
Mhm.
generator is used whenever we want.
Okay. So let's just have some questions from standard itself. You have done pretty good, experience in this high performance, high density. So what do you mean by high density standard cells? How they are
Tracks
different
get
from high performance?
high performance area is not matter, and high density area matters. So high density number of tracks will get reduced, and for
Mm-hmm.
high performance tracks are more.
So
So
you
that is
mean
the major difference between the high density and high performance.
that's it?
High performance is first priority, area
Mm-hmm.
is the second one,
Okay.
and in a high density area is the second priority, first
So,
priority.
okay, if I fix the
And
number of tracks for both HD and HP, so what kind of cells will come under the high performance and what will go in under high density? If I fix
can
the
you
number
repeat
of
the
track, if I fix the number of track, then what kind of cells will I consider in high performance?
what kind of a cells means everything, all standard cells like
No, no, no.
inverters, buffers.
I meant to ask something else. I mean to say that if I'm fixed, so the basic difference you're saying that when I'm having two different type of standard cell, that is one high density and high performance, right?
Yeah,
So that means the tracks and number of tracks are more in high performance. That means the standard cell height is more in high performance.
yeah,
But I'm saying that if I'm fixing a number of tracks in a library, so if I'm saying that I have fixed the number of tracks and I have only one architecture with the fixed height. So what kind, if I have inverter, buffer, flops, other things, level shifters and everything else. So what kind of cells actually consider in the same thing under the high performance requirement, or some what kind of cells go under the high density one? Like if I'm fixing an architecture, where for which particular which cells, you can give any example, it's not like you have to mention all. What kind of cells are actually considered for high performance, where we go for performance more than the area?
HVT, LVT, you are talking about that.
No.
Because in high performance, the length and widths are more, so their metal widths are more. But in high density, we have to go everything with the minimum spacing, minimum metal width, minimum metal pitch.
Okay. Okay, so okay.
Actually,
Other
by default, in a high density, by default, the size of a device is already less. The
Mhm.
length, width, everything is less.
Yes. No, actually, I think I meant to ask something else, but I misinterpret or said, or I mean, miscommunicate the question. I meant to say that if I'm fixing a library for a particular, say, suppose if you are talking about like 5 tracks or 6 tracks, so I'm considering one 6 track library, and I'm asking in that particular track library, what type of cells are actually those cells where you opt for performance more than the area. Suppose if I have a buffer, I have a flop, I have a AOI, OAI, or some kind of cell or some sequential cells. So what are the cells where we look for performance more? If I'm going for performance, what kind of cells are critical cells? That was my question.
Critical says you're asking.
Yes.
So critical, I personally felt like a Mercs and D flip-flops.
Mm-hmm. Okay.
Yeah, those two cells I felt little bit critical.
Okay.
If the number of tracks are less in a high density, so
Mm-hmm.
actually it is difficult for routing.
Okay.
And Merck schematic is already different, and so many devices are there, so their connections are lengthy. So sometimes we have to use the metal 2. Actually, in a standard cell, we have to use only the metal 1 tracks, but in some cases, we have to use metal 2 as well.
Okay.
Not for Mercs,
So,
but at least for a D flip-flop, we have to use.
mhm. So
Even
what
in
is the minimum height of metal you have used? And what's the maximum height of metals you have used? From which level to which level you have been through?
which level, means for metal 1, you're asking, it is like
Yes, it's kind
0.3.
of. Till what height you have been through, like metal 3, metal 4? What you have observed?
In standard cell, I did everything in metal 1 only. But
Mm-hmm.
in one case, I used metal 2 for D flip-flop. In a 16 nanometer, there I was getting lot of that M1 G0 error. There
Mm-hmm.
that M1s are creating some circles. So to remove those things, there I used the tracks was less, and so there I used
Okay.
metal 2 only for
Okay.
one track.
Okay. So, okay. So, what's the difference between other than okay? What's the trade-off between high density and high performances?
I didn't get the question. Means basic difference.
I mean, if I am moving from high density to high performance, what I have to lose? Where I will be trading off, or where I will be compensating the things?
Tracks.
And
First thing, the tracks, you will get more tracks.
mm-hmm.
That is the one thing.
Okay. And other?
That is the only one thing, that tracks you will get more.
Okay. And how do we calculate the area of standard cell?
Area, complete area.
Yes.
Area means height is fixed,
Yes.
and if you are asking about the width, it is the multiple of the poly pitch.
Okay. How do we calculate polypeptide?
Poly pitch, it is already given in the DRM. So based on that,
No. I mean to
we
I
can
mean to say, if it's not about DRM, if you are jumping from different foundries to different foundries, that's a different thing. That it's give. But how are we calculating the poly pitch? I mean, what do you mean by poly pitch? That's my question.
poly pitch means actually we have a gate connections. Like whenever we have OD, like
Mm-hmm.
rectangle kind of OD, and poly is crossing, right? So when the poly is crossing to the OD,
Mm-hmm.
we say like it is the transistor. So when we abut two devices like drain to drain, source to source, or two
Mm-hmm.
nets are different, then we have to abut.
Okay.
So there is a difference between the two poly from one edge to other edge, or from center of poly to the other center of poly. So what
Okay.
is the difference between them? Those two polys, it is the poly pitch.
Okay.
Or else you can say from axis that we have, like x and y axis, from y axis to the first poly.
Okay. And
But
how
that
do we
poly
calculate the height of standard cell?
pitch into n minus 1. N is nothing but the number of track. But
Okay.
finally, that heights we are deciding in the practical, like how many tracks we required.
And how do we decide that?
First we have to check all the schematics, like their length and weights. Like if I talk about the FinFET, so like if one device is getting like 3 pin device, one the other transistor is like 4 pin device, if another is a 5 pin. So based on that, we have to check first what should be the minimum distance between the two devices like PMOS and NMOS, and what are the connections. Different connections are there. So different connection means that number of tracks we have to define, how many tracks we need between two devices. So that devices we have to fix first, and then rest of the things we have to calculate. Calculate means like for NMOS at least minimum 2 tracks for powers and 2 tracks for grounds also. And power tracks we are keeping little bit minimum than the metal width.
Okay.
Finally, everything is depends on the different
Any other
connections.
thing, I mean, any other thing than this, other than the routing perspective, do we have any other point that how we calculate the standard cell height?
That only I know, like pitch into track minus 1.
Okay. So, do you know beta ratio?
No.
Okay. Okay.
Beta
So,
ratio, that beta ratio I don't know. That 2:1 that we have to check that one.
okay. Okay. So, okay. Let it be. Could you please explain what's back-to-back diode?
Back-to-back diodes are connected between the powers or ground. Whenever the level of powers get changed, there we have to use that back-to-back diode.
Any other name for
Means
back-to-back
from,
diode?
you can say like a level shifter kind of thing. It changed the level of powers from one VDD1 to one another VDD2, or ground to another ground one.
Okay.
It is kind of level shifter.
What's the critical net in a level shifter?
In a level shifter, only the power was there. Actually, two powers are there. So both
Mhm.
the powers we have to differentiate from each other. Otherwise, it will get short circuit. The two
Okay.
anvils we
So,
have to separate.
you have designed level shifter according to standard cell or according to some other kind of layouts like you have mentioned?
It was based on the standard cells only.
Okay.
But based on standard cells means actually what generally we do, the in the standard cells we have to create some template part,
Yes.
right?
So, what kind of
In a
template
template
did
part,
you use?
a template is created by us only. So
Mhm.
what kind of means normal based on the heights only we created, like some base layers are there, and polys are already there. So we just have to instantiate those PMOS and NMOS. After
Mhm.
that, you can hide that base layers from property, and then just place it in the template part. So actually every time we don't need to means draw each and every layer, just calculate, means from the scale we have to fix the heights, everything is already fixed, just instantiate it and do the mosaic.
Okay, but I mean to say
So
when
all the layers you will get
no,
by
no,
default.
1 second, 1 second. I mean to say when we are designing a template and we are just instantiating everything, it's okay. But I want to ask, when we are designing a level shifter, and for a person who hasn't seen the level shifter or which we use, how will it look like? Like what kind of cell it will be? Will it be using having different height structure than normal inverter? Or will it be having some other things, or we have an n-well or structure different than normal cells? How will it
It
look
looks
like?
like standard cells only.
So in what height it will be done?
It
Like single
was
height, double
one.
height, triple height? What height have you done?
Okay, I completed in a 16 nanometer. So the in 16 nanometer height was a 1.5.
1.5 height.
Yeah.
Okay, I think I didn't relate to it because I haven't seen the 1.5 height actually.
Okay.
Okay. And the architecture, whether the well was continuous or the end well was broken, whether it was VDD based architecture or VSS based level shifter.
Two different powers, but ground was same.
Okay. So did you notice anything different other than when I'm just taking a normal inverter or any flop structure? Did we
I
focus
didn't
on
get.
somewhere or did we add something extra?
Means can you repeat the question?
I mean to say, when we are designing a level shifter or when you have designed a level shifter, and if I'm comparing the basic template architecture of a level shifter with an inverter within the same techno, within the same requirements. So, did you notice anything different? Other just like you mentioned that when I'm designing an inverter, it is in one height, but when I'm going for a level shifter, it is 1.5 height, right? So just similar to this, do you notice any other thing we took care while designing level shifter? And or how did you design the level shifter? If you have a paper or something, can you just give me the layers or something like that? If you have, it's
Okay, okay,
okay.
sure, sure.
If you don't have, then just tell me verbally. It's fine with me.
Actually, it completely looks like a standard cell, but height was completely same. But
Mm-hmm.
yeah, in a standard cells, like we are always try to keep the ODE continuous. Okay,
Mm-hmm.
but in a level shifter, it was discontinuous, so it looks little bit different.
Okay.
But the height was same.
Okay. Any other part from height was just an example I gave. Any other thing which you have noticed? Like how did we route the different powers? You said now we have two different kind of VAD. So how did we
Yeah.
provide the routing to it?
First, we have to separate those devices which has a different powers.
Mm-hmm.
So just we have to keep them separate and we can supply the power
Okay, so how you are separating them?
by keeping the minimum space between the two wells.
Okay, so
Uh,
you do use the two N wells. Actually, that was my point.
yeah, okay.
Okay.
Like in a 16 nanometer, I think zero point 0.8 is the minimum space between the two well. I
Okay.
don't remember
So
exactly. I think it is
okay,
zero
okay.
point 0.8.
So you have worked in 16 nm on CMOS or in FinFET, or I mean some
FinFET.
FinFET, 16 nm FinFET, and what other type of devices you have worked on? So you worked,
Only, yeah.
yeah, only
What type of devices means?
like just like you said, na, that you have worked on 16 nm in FinFET. So the next techno, your 40, 45 nm, were those CMOS or FinFET or FDSI?
FinFET, I worked on 16 and 7 nanometer.
Mm-hmm.
And CMOS in a 28 nanometer, 40, 90 above 28, it was like normal planar CMOS.
Okay. So what's the difference you've seen between the FinFET and CMOS layouts?
DRCs are more in FinFET.
Mm-hmm.
Some layers are getting increased as we go in the lower node.
Okay.
So as layers are more, so DRCs are more, and it is completely fin based. So we have to place the device based on the fins only.
Mm-hmm.
That fins we have to maintain.
Okay. So, did you see any kind of disadvantages while using FinFET layout while comparing to the CMOS layouts? Any kind of less flexibility or any other thing?
DRCs are more, so actually it is more time consuming. Like if I say about if I compare about means between the 16 nanometer and 7 nanometer, so in 7 nanometer, lot of layers are increased. M0 layers are there, and M0 layers are there. So cut M0 is also there. Cut M1 is there.
Mm-hmm.
Cut OD is also there. Like error layer is also there wherever the part is not getting recognized. So each and every layers are increasing the lot of DRC. So that DRCs are time consuming, more time consuming. That one disadvantage I saw. Again, if we go in the lower nodes, so like the double patterning is also there. So we have to mask the each and every layer.
Okay, okay.
That is also time consuming.
Mm-hmm. So, theoretically, what's the difference between CMOS and FinFET?
A channel with channel length theoretically, like 16 nanometer and 28 nanometer is nothing but it says like a length of the channel.
Could you
So
please explain a bit more?
uh, like 180 nanometer is there, 90 nanometer, 16 nanometer. Okay, that 180 number says the length of your channel. Okay,
Mm-hmm.
180 means more number of a channel, means the channel length is more. If 16
Mm-hmm.
nanometer means it is the channel 16 nanometer. So 16 nanometer, suppose I have a one IC, 180 nanometer channel, I can place only the two devices, 180. But if I use the 16 nanometer, so I can use the n number of means multiple of 16 nanometer devices. I can use more number of devices. So the channel length will decrease the size of the device.
I got a bit confused. Could you please repeat?
Okay, that actually the technology number
Mm-hmm.
describes the length of the channel.
Yes, correct.
Okay, yeah. So length of the channel means like 16 is less than the 28 or 40. Okay, so
Got
if
it.
the length of a channel is less, so the size of the device is less. So we can place more devices in the single chip.
Mm-hmm.
So that is the one difference theoretically.
No, I actually meant according to the architecture. Just like when we discussed the FinFET versus CMOS layout, so you have seen the different layers. We needed the cut layers. We needed different. We saw see the different DRC. So according to that, I meant to ask about the difference in architecture. Theoretically, what kind of difference in architecture?
Okay, so normally like maybe you are asking like
Yeah,
leakage is
when you
less
are
in the
seeing the
FinFET.
channel, when we are seeing the channel of CMOS, and then how it will look, and when you're seeing a channel in a FinFET, how much different it will look. That was my point.
Actually, it's a 3D structure in the FinFET.
Mm-hmm.
Okay, and in the planar, it is like only the plane, so we can see the channel clearly between the source and drain as we apply some inputs.
Okay.
And FinFET also the operation is same, but it is the channel is completely wrapped, or you can say it is completely covered by the gates, multiple gates.
Okay.
So the control over the channel in the FinFET is better than the planar MOSFET. So leakage is almost less, or you can say it is the negligible in a FinFET.
Okay.
So
So
leakage
how,
is less
when we
in
are having a 3D structure, how does it help in reducing the leakage?
in the 3D structure, actually, the channel is first thing completely covered by the gate. Okay,
Mm-hmm.
so the channel length and width is completely controlled by the gate. Okay, so like VGS is greater than VT, then channel will get created and conduction starts.
Okay.
So that channel part is completely controlled by the gate. And in the planar, only the one gate is there. In FinFET, the multi-gate. And the second thing is like it gives the 3D structure, so we can add multiple devices with the same power supply, same electricity, same power supply. So that
Oh,
also avoids the power dissipations.
okay, okay. So
It
what?
is just everything just because of the multi-gate
Okay.
control over the channel is good.
What other things are improved in FinFET in comparison to CMOS?
Speed is more as the channel device size is less, channel sizes everything is small. So
Mm-hmm.
the speed of the FinFET is better than planar MOSFET. So number of features we can add in the FinFET.
Just like.
Performance is also features like in the mobile we know how many features are there. So those features we can add in one chip. Number of more features
So
we
that
can
will
add.
be an SoC level, right? If I'm having just a FinFET, can we add any feature in that?
No features layout point of view I don't know.
Okay. Okay. So please continue. The performance can be increased.
Okay, performance is also increased and like drain induced barrier lowering, one thing is also improved in the FinFET. As we
Mm-hmm.
increase the drain voltage, so the channel is getting break from the drain side, and some pinch off means pinch off is occurring. So that
Okay.
thing is also improved in the FinFET.
Okay. So currently, how does the pinch off looks like in FinFET?
In FinFET, it is continuously actually operating point we need very less. We don't need a more voltage like 1 or 1.5 volt is also sufficient for the FinFET. But in the planar MOSFET, the voltage is more. And so even with the less operating voltage, we can turn on the device and conduction will get start. So no
Okay,
need to increase the VD drain voltage.
got it. So could you please explain a bit more about DIBL and CMOS?
Actually, what happens generally as we apply some input to the gate,
Mm-hmm.
so our actually when a VGS is greater than the VT threshold voltage, then only the channel will get created between the source and drain, and then conduction will get start. Okay,
Got
but
it.
generally our source, yeah, but generally our source voltage is zero. Okay, so
Mm-hmm.
VGS and VDS, we have two types of voltage. We are connecting two batteries between gate to source and drain to source, and source is always connected to the zero. Okay,
We are
so
taking an example of
uh,
NMOS right now, right?
yeah,
Enhancement type NMOS.
yeah, a positive VGS we are applying,
Okay.
enhancement you can say. Okay, so like then channel will get create and then conduction start, but we have to also apply the VDS. Okay, but as we increase the VDS, so more
Mm-hmm.
charges will attract from source to drain and more current will flow. Okay, but there will be a point after that. Even if you increase the VDS, there will be no increase in the current, drain current. Okay,
Okay.
so there some channel will get break because of the large voltage across the drain current. So some channel will get break from the drain.
Okay.
Okay, so like suppose your source voltage is zero. Okay, so VGS. So and your gate voltage is like suppose two. So two minus zero is two. But here VDS. Supposing some by mistake your source voltage got increased and so that VDS difference uh, can affect the performance also. But the voltage across the more that more voltage across the drain will break the channel. So some discontinuity will be there across the gate and some channel will be break. So whatever the previous current is there, it will be same as it is. And even if you increase the drain voltage, there will be no increase in the drain current. Even if you increase the drain voltage.
Okay. What are the other short channel effects you have known about?
Uh, impact ionization is there.
Mm-hmm.
Impact ionization. Uh,
What is it?
Impact ionization means From the channel, actually our P substrate is usually generally connected to the ground. Okay, so that ground and in the across the drain, because of the large voltage, some holes will also be there in the channels also and across the drain also. So that the P substrate will attract some holes from the channel or say from the drain part. And one channel will also create from drain to the P substrate and some current will flow in that direction. But generally, it should not be there. That is the impact ionization, and hot electron effect is also there.
So
Hot
impact
electron effect,
ionization, okay, impact ionization is little bit related to latch up right now.
yeah, latch up.
Okay, so are you saying that both concepts are same, or they are just similar, or they are exactly same?
They are similar.
So what's the difference between them? How much latch up is different from impact ionization?
Latch up is mostly occur due to the parasitic BJT gets triggered on.
Mm-hmm.
So, and even in the NMOS, if I talk about the NMOS, we have a P substrate and two N plus dropping for source and drain. Okay, so that source and drain, just in the NMOS, this impact ionization can occur, but for parasitic BJTs, we need a PMOS as well. That N-well layer we should have. Like the parasitic BJTs like NPN and PNP, so that N-well layer should be there to form the parasitic BJTs.
But if we are having a CMOS architecture, then it will be having N-well layer, right? And
In
anyway, we are
CMOS, it is
providing the
different.
source connections, so we are anyways giving the doped architecture for it, like N plus and P plus,
Yeah,
just to provide
then
the
we
connection to the
can.
body, right?
Yeah,
So,
yeah, it can be there. If we provide the body, then it can be there.
but it can be there or it will be there.
It will be there.
Then now we have a source connection, we have normally body connection, we have a gate connection, and we have a drain connection with these four terminals in CMOS. So total we have right now 8 connections. Now can we just go through the latch up again?
Yeah. So latch up for the latch up, actually it occurs mostly when parasitic BJTs get triggered on. Like so, to form the BJTs, parasitic BJTs, we require 3 types of a material like NPN or PNP. So those are if wherever these 3 layers are there, their parasitic BJTs will get triggered on, and it will create some low impedance part from power to ground, and all the charges will flow from power to ground and ground to power.
Okay.
Through the BJTs. Whenever
And
there will be
what kind
any
of triggers
spikes,
do we have to start the
trigger
latch
some spikes in powers, grounds, and outputs also.
Okay. So if I give a trigger, what kind of trigger will be at if I'm going for a VDD, what it will be, or what kind of trigger it will be for a VDD, and what kind of trigger it will be for a VSS?
If trigger is from the power side, then current will flow initially from power to ground and then ground to power.
Okay.
We just have to trigger any one of them. If you are triggering from ground, so then first ground to power and power to ground, and the process will be continuous.
And how do we control it?
We have to reduce the resistance. Other solutions are also there, like we can use the guard rings, so we can like minority carriers will get will get blocked. The guard rings we are using so that minority carriers will not flow from one device to other device. For PMOS different guard rings and for NMOS different guard rings. So PMOS to NMOS, that minority carriers will not flow. And to reduce the resistance, we can add more P-well and N-well contacts. Taps we can connect. A deep N-well we can use deep N-well or STI material. ESD also we can use ESD protection circuit.
Okay.
And
what is ESD protection, and how do we use
ESD
it for?
Actually, our human body has some means whenever we walk and we touch to any steel material. Okay, so
Mm-hmm.
our body get charged when we walk. So even if we touch to anything means where we can generate the short circuit, it will get short. So generally, just from the small fluctuations that ESD can occur, some short circuit. So
Okay.
there we have to use the ESD protection.
So what kind of ESC production circuit it is that we are using for laptop? What will be
That
its
I don't
circuitry?
know.
Okay.
That I don't. Maybe actually we have like a human body model, machine model.
Mm-hmm.
So
So what's the
that
architecture
exact.
of a guard ring?
Guarding means actually it is like a rectangle kind of thing or
I
one
mean, I
strip
mean to,
also.
I mean to ask what it will contain. Like we are having a guard ring, what kind of layer it will consist?
It's depend on the technology. OD
Just
is
give me
fixed.
any,
If
just give me any CMOS technology. Let's just go on
uh,
the top, right? 180, 90, whatever you remember.
okay, OD will be there in the guard ring.
Okay.
Some masking layer like if it is a P type of device, then P implant will be there.
Okay.
NVEL will be there.
Mm-hmm.
Some vias will be there via
Okay.
some small contacts for metal will be there, metal one if it is like about 28 nanometer, metal one,
Okay.
some implant layer and well, these are the layers, basic layers.
Okay. How guard ring is different to from a tap?
It is same actually, almost not same,
Okay.
it is completely same, you can say tap cell is nothing but the guard ring also.
Mm-hmm.
Like in analog we says like guard ring, but in standard cell it is a tap.
Okay. So you mean to say only the difference between its sizes and where we are using them?
Yes.
Okay.
In a
What's the full
standard
form of
cell,
DRC?
sorry,
What's the full form of DRC?
design rule check.
And what do we do by using it? How does it help?
The use of a DRC, it is like a minimum requirement for the fabrication.
Why
So
do we
it
have to
says like
define? Why do we have to define the minimum requirements?
for a better quality of the product. Like
Okay.
if you don't follow the DRC, there can be some short circuit of the two metals.
Okay.
Actually, DRC says like what should be the shape of the layers, what should be the minimum spacing between the two layers.
Mm-hmm. So let's just say I'm using maximum spacing rules instead of the minimum spacing. I'm having a different distance. But how does the shape of a layer help me in fabrication? Why should I focus on the shape in DRC shapes that are given? Even if I have a particular proper distance, even more than the required distance between it, between two layers. I mean, the same layer with two shapes. But why do we have a fixed shape?
Fixed shapes to reduce the area. If you are taking like metal more than the minimum, then it is always good. There will be no EMIR, other things. It is always helpful. Like even for the better yield, we are following the DFM, design for manufacturability. If you are taking the more shape, then no issues. But finally, it's depend on the area.
Mm-hmm.
To
So
reduce the
how
area, we have
DFM
to
different
define.
from DRC?
DFM is more than a DRC. Like suppose difference between two metal is like 0.32. So DFM says like take it little bit more than 0.32 for better yield.
Okay. What is LVS?
Layout versus schematic. So whatever the shapes you have drawn, it is based on the schematic. So both are getting matched or not. That is the LVS.
And what are the inputs for an LVS?
Net list of schematic,
Okay.
schematic netlist,
Mm-hmm.
layout netlist, and rule deck file.
Okay. And what kind of error do we generally see in a LBS failure?
Actually, in LVS, actually I'm using Calibre. So two types of error I'm able to see, like one extraction result and a comparison result. So in extraction, like software check conflict errors are there, and in the comparison, port check, port errors, instance error, property error, label. Okay, that label is in the extraction. Net error. Those are the errors.
So, I mean, could you just explain a bit more? What are the port error? What are the instance error? What are the net errors? And what's the fourth one you just said?
Port error means actually we have inputs like suppose I1, I2 or output VO. So those are the port actually. If it is not properly defined in the layout, so you will get the errors. Means our label or say some pins are not properly placed. That is the port error. Instance means sometimes it happens like suppose you have a 4 device in schematic, but only 3 devices are there in the layout, so it will throw like missing instance. Still, if you have a 4 devices in the layout, so but because of some wrong connection, it will throw some instance error also, missing instance.
Okay.
And property
So,
errors means suppose if length and width is not properly defined, then also it throws like a property errors. But sometimes I felt also like if connection is not properly done, then also it shows the property error.
okay. So, what are the net errors?
Net errors means nets are not connected properly, or say some connections are pending. It is open or short.
Okay. So, which one do we resolve first? Open or short?
I personally I do the shorts.
Why?
Short will help to check like what are the connections are required. Like if you
Okay.
open nets, you will do the routing, so it can increase the errors.
Okay. 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 One more good thing. What do you mean by layout dependent effects? What comes under this family?
EMIR actually,
Layout dependent effects.
uh, like a well proximity effect.
Yeah.
Okay.
What is well proximity effect?
Well proximity effect means while doing the ion implantation, actually suppose I have a 5 devices.
Mm-hmm.
Okay, and I'm doing some ion implantation. So while doing the ion implantation, so first and last device will get more ions. That ions will hit to the n well and will deposit to the corners devices. So that corner
Okay.
devices will get more ions. So VT for the corners one and the in between there will be different. So
Okay.
in between devices will get the uniform ions that during the ion implantation. So between in between the devices are there, they will get the uniform ions, and VT for them it will be different. VT threshold voltage will get affect.
Mm-hmm.
Threshold
And
voltage
any
for
other
in
layout
between.
dependent effect?
Yeah. Uh, Antenna effect.
What is antenna effect?
Antenna effect is actually while doing the plasma etching in the
Mm-hmm.
lengthy nets which is connected to the gate. During the plasma etching, lot of electrons will be there in the lengthy metal. So those electrons will hit to the gate terminal, and the gate terminal will get damaged.
Okay. So can we
Uh,
fix it after fabrication?
Sorry,
Can we fix the antenna effect after fabrication?
no.
Why so?
Before actually, it's
We did some
depend.
corrections, right? When we have some issues, we generally use for correction in fabrication. So why cannot we correct antenna effect after fabrication?
After fabrication, if your device is completely done, so if some let me explain first what is the antenna effect, how it cause actually. Some solutions are there also, we are using n type of a reverse bias diode in antenna effect to resolve those error. Like, so what reverse bias diode do? So in the plasma etching, reverse bias diode works for the higher voltage. So if voltage is very high during the plasma etching, all the charges will flow towards the ground only. Okay. If it is the if we are not connecting any diodes, or we are not doing anything as a solution, as a remedy, and directly devices are means already there for the went for the fabrication, so that charges will hit to the device directly, and device will get damaged completely during the fabrication only.
Okay.
So in the plasma etching, charges are more. So during the fabrication only, device will get effect. Maybe it will get damaged during the fabrication only. And this is the only reason we are using the reverse bias diode, not the forward bias diode. Forward bias diode works for the less voltage. If during the fabrication, that forward bias diodes will get damaged in the fabrication only. Even though if that diode is not get damaged during the fabrication, anyhow in some cases, suppose, and when it will come under the real operation, like forward bias diodes works for the less voltage, like say suppose 0 to 5 volt, and during the real operation we supply suppose 5 volts, so that the forward bias will get turned on and all the charges will flow towards the ground. Your our original device will never get turned on. But in the real operation, if we are using the reverse bias diode, so like 0 to 5 volt, reverse bias diode will not get turned on, so your original device will get turned on.
Okay. So what is deep anvil?
Okay, deep anvil, suppose I have a 5 NMOS, out of them 4 is connected to the ground. There are taps, there are body connections, you can say. Okay, but out of them 4 is connected to the ground. There are taps, but fifth one is not connected to the ground. It's a body. So that fifth one we have to separate. So that fifth one we have to keep in the deep anvil to avoid the latch up.
Okay. But still, according to the architecture, what it will look like?
It is like a level shifter. We have to separate them.
Okay.
Their anvils will be different. Means anvils means their well will be different if their powers are different.
Okay. What is layout matching technique?
Layout matching to minimize the process variations. Uh, like uh, During the fabrication, we are getting some etching problem, like oxide thickness or doping, ion implantation. Those variations comes under the focus. So to avoid those, like matchings we are using. So we have two types of matching, like common standard and interdigitization. So for generally, if I talk about, means whenever we say like analog layouts, analog is like a bunch of current mirrors and differential pair. So for current mirrors, we are using interdigitization method, and for the differential pairs, we are using a common centered method.
Okay. So which one do we focus more on? What's the, I mean, we have different type of matching techniques. So which one is more preferred? What's the, I mean, advantages or disadvantages one on the another?
Uh, I think common centered method. Common centered means actually it is in the multiple rows, but interdigitization is like only in the one row. So it increases the size of the device. And for the common differential pairs, we have different two types of voltages, like V plus and V minus. So their routing also we have to match in the differential pair.
Okay.
And in the current, the nets are little bit lengthy.
Okay. What is signal integrity?
Sorry, I don't know.
Okay. What's the difference you have seen between AMS and digital layouts?
Digital layouts are based, means height is fixed.
Mm-hmm.
Digital layouts are based on the standard cell, so their heights is fixed. It is continuous kind of thing. If it is a level shifter, then only otherwise it is a continuous. But in the analog, like tap cells are like we are keeping PMOS in the different taps, NMOS in the different guard rings.
Okay.
It is like guard rings we are using in the analog, but in digital tap cells are used in a strip kind of thing. And yeah, that is the thing, most major thing.
Okay.
Area we need little bit more for the analog. For digital, it is like square or rectangle. It is fixed.
Okay. So you know EM, right?
Yeah, electromigration.
What is it?
Due to the high current density, electrons will break their bond and they will create some vacancy or they will deposit. Also, they will grow. So, uh, like a goose or a bump kind of structure, they will create helix kind of structure.
Okay.
So it may happen like instead of a 2 milliampere currents, 1 milliampere will flow, or it can be more than that. If a
Mm-hmm.
high current density is there, so like their temperature will get increased, resistance will
Mm-hmm.
get decreased, and current will increase. So this process will be continuous, and finally your metal will get damaged.
Okay.
So it is always better to first check the requirement and based on that take the metal with. As I
So
told,
what?
we already discussed like what we if we take the more than minimum. So solution is like just take the little bit more metal with, or
Okay.
else higher metal with metal stacks we can use.
Okay.
As a layout engineers, we are not handling, but frequency also we can reduce some power with requirement voltage we can reduce as a circuit designer.
Okay. Okay. You have also worked on LDO, right?
Yes,
So you worked on LDO with according to standard cell architecture, according to analog architecture.
analog.
Okay.
Error amplifier is there in the LDO.
Mm-hmm.
Error amplifier is there, capacitor is there, resistors are there.
Mm-hmm.
So except the payments, these three things we have to use it, everything I did as per the analog only.
Okay. So what's the difference you have seen between the analog layouts and standard cell layout?
Area first thing, like for analog area is required more, and in a standard cells PMOS and NMOS are abutted. It is
Mm-hmm.
continuously abutted. Like half portion is for PMOS and half portion is NMOS. It is compulsory. But in the analog, PMOS we have to keep in the separate guarding and NMOS we have to keep in the separate guarding.
Okay.
In the analog, current mirrors are there, the differential pairs are there. So matching we have to do in the analog, which is not there in the standard cells,
Okay.
in the digitals.
Okay. What is density checks?
To avoid the metal erosions, that density across the chip we have to maintain.
Mm-hmm.
Like whatever the areas we have, based on that we have to check how much ODs are used, how many ODs are used. So percentage we have to check. It is like more than 50% or 65%, how much it is required. So based on that we have to maintain that density.
So what will happen if I have a metal less than the required density?
That metal erosions occurs actually etching problem.
Okay. So what kind of standard cells you have designed?
what kind of means high
Mm.
performance, high density?
No. Just the cell names like inverter, buffers. You mentioned data
Inverters,
set.
buffers, yeah, inverters, buffers, NAND, and or mux, D
Mm.
flip flop.
Okay.
Standard cells actually in layout they are giving any name. So for standard cell it is okay, but if you ask like analog, we are
Mhm.
not able to understand what is this circuits, and mostly specifications they are not providing. Everything is like confidential. So
Yeah, it happens.
like in a office, few of the employees have AMD access. They are
Hmm.
unpaid. They are unpaid, but they have access. But they are not able to use any technology. It's a confidential.
Yeah, according to the project requirements, according to the company requirements, things changes, right?
Yes.
It's okay. So yeah, that's all from me. Have a good night.
Yeah. Good night. So currently you are teaching in a RV VLSI for all.
No.
Okay.
And you're joining VLSI for all right now?
I joined in December, I think.
Okay, current December, right? The 22.
Yeah. Yeah.
Okay. So you're trying to change the profile?
Try to change means actually I already resigned. I'm at home only.
Mm-hmm. So you
I
already
am
have this
applying.
experience in layouts and you're again, I mean, just improving the expertise, or what's your purpose right now?
Uh, First, I need a job in a layout only.
Okay.
AMS. I
Okay.
applied in different companies like Synopsys. As
Mm-hmm.
of now, only Synopsys have a vacancies, but I didn't get any call till now.
Things are, man, going less like this right now.
Less means actually I don't know what to say. I someone already referred me, so
Mm-hmm.
now whoever is referring, they are getting like duplicate mail.
Yeah. I'm
So
not
I don't
sure.
know how
I think
to.
I have heard your name, whether you have sent your resume to me through LinkedIn or I think I forwarded it. I'm not sure. I think it is you or it's some other Avinash. I'm not sure.
Let me check.
I'm seriously not sure.
Okay. You are from which location?
Noida?
Okay, Shefali, na?
Yes.
Shefali Sharma. Okay.
So you are the one same, right? You sent me your resume.
No, I didn't share, but yeah, I talked on LinkedIn.